All right, so we're going to continue our discussion of classical groups by returning a little bit to a review. We've decided that the classical groups that we're talking about are groups of matrices, right? The classical groups are groups of matrices. And we are then understanding that the group is a group under matrix multiplication. That is the group operation, right? It's closed under matrix multiplication. Of course, all of these are invertible matrices, which, by the way, means the determinant of the matrix, right, is not equal to 0. And but other than that, the field over which these matrices are made, the three different choices we have are the real number field, the field of complex numbers, the non-commutative division algebra of the quaternions. Those are the three that we are considering as being entries in our matrix. So we can have matrices of real numbers, matrices of complex numbers, or matrices of quaternions. What's interesting, by the way, is the fact that quaternions are non-commutative does in fact show up when you try to talk about the determinant. It's hard to make sense of the determinant of something when the numbers don't commute. You can find equivalent forms of a single matrix where if you calculate the determinant the usual way, you would have different orders of operations. And that non-commutativity creates a tremendous ambiguity in the idea of a determinant. I'm going to show you how to get around that in this lecture. One of the other things I do need before we can really talk about the classical groups, because ultimately we're going to be talking about the relationships between the classical groups, one thing we need to understand is the representation of complex numbers and quaternions in terms of matrices themselves, which is a really interesting idea. But let's cover that and see how that helps us with ultimately understanding classical groups. So we consider a complex number a plus ib. Then I want to make the replacement. I want to turn this complex number into a matrix that will represent the complex number. And as such, that means that if I were to multiply two complex numbers, c plus id, if I could find a matrix that represents this complex number, and I matrix multiply it by the matrix that represents the c plus id complex number, the resulting matrix should represent the product of these two, which is going to be ac minus bd plus I bc plus ad, right? So this complex number should be represented by that matrix, right? I need to find a matrix structure for this, and it's not too difficult, right? I take the unit 1. Remember, the basis, you can think of a complex number as a real vector space where the basis vectors are 1 and I. So 1 is going to be converted into the identity matrix, and I is going to be converted into the sort of the counter, this matrix here, this anti-symmetric, the simplest anti-symmetric matrix you could have. And those two together, I would say that I'm going to map the complex number. I'm going to map the complex number a plus ib. I'm going to map it to a matrix. And the basis mapping is, and remember, if you're ever mapping a vector space, if you know how the basis vectors map, you know how everything maps. So the map of the basis vector gamma 1, I guess, is that, and the map of I, gamma sub of I, is that. So the gamma sub a plus v is going to be a times 1, 1 plus b times 0, 1 minus 1, 0, which is going to be a minus b, b, a, right? So that is how you map all complex numbers. And notice I'm now mapping a single complex number into a 2 by 2 real matrix, and that's really critical. So for example, if I had a 2 by 2 complex matrix, right, a plus I b, c plus I d, e plus I f, and g plus I h, I could map that into a 4 by 4 real matrix that would look like A minus B, B, A, C minus D, D, C, E minus F, E, F, and G minus H, G, H. And so now I've gone from an element of the general linear group of 2 in the two complex numbers, I've gone to the general linear group of 4 in the real numbers, right? Important notion to understand. We can also do this for quaternions. And the story is pretty much the same. A general quaternion can be written like this. If my mapping, and so I've got to map the 4 basis vectors, which is 1, I, J, and K, into some kind of matrix. Well, I'm going to map 1 into the standard unit matrix. I'm going to map I into minus I times the Pauli matrix, the first Pauli matrix. So it's minus I times 0, 1, 1, 0, which is equal to minus I, 0, 0. I'm going to map J into minus I sigma 2, which is minus I 0 minus I 0, which is 0 minus 1 minus 1 1. Wait a minute, minus 1 is 1. I squared is minus 1. No, this is minus 1 1 0, right? And then K will be mapped to minus I sigma 3, which is minus I 1 0 0 minus 1, which is minus I 0 0 I. I think I got that right. Now notice here, what's interesting is this I here is the I of the complex numbers, right? This I here is the I of the quaternions. The point is the final result, obviously, is going to be a 2 by 2 matrix of complex numbers. And in fact, I've blown it up here so you can see it. This quaternion will map to this complex number. See this I? This 2 by 2 complex matrix where these I's are here, right? So those I's are from the complex numbers. Now, if I were to blow up this 2 by 2 complex matrix into each of these complex numbers into their 2 by 2 real matrices, I would end up with a 4 by 4, which means that I can take a matrix of quaternions, some matrix of quaternions, Q, 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 say there's n dimensions, I can convert it to a member of the general linear group of 2n dimensional complex numbers, and that can be converted to the general linear group of 4n times real numbers, right? So I can create these I can move between the different matrix general linear groups using this prescription. But and the point of this though is I can calculate the determinant of that, and I can calculate the determinant of that. It is not too logical to talk about the determinant of the quaternion, so I can sort of bootstrap a definition of the determinant for a quaternionic matrix by doing this method. And there's actually a lot of other things that you tend to pull the quaternions into complex numbers, and you show a lot of the relationships between these groups using this logic. So I wanted to introduce this logic here. Okay, so let's move on. So Gilmore then moves on to talk about metrics in the carrier space. He doesn't literally say it this way, but he uses the word metrics in the carrier space. For those of us who have done the What is a Tensor series, this word here is what we were calling the inner product, right? The inner product in the carrier space. And if our carrier space is some vector space of n dimensions, right? Remember how I used to write this? It has n dimensions, it has some basis, e, mu, and then I would write down the field that it's in, right? The field that it's in. And for general relativity, it was always the real number field. But we're going to allow this to be, of course, real, complex numbers, or even quaternions. So if I have a vector space like that, then I have a defined addition and a defined scalar multiplication involving this field and any vector in the vector space. We know that. The inner product now allows me to take two vectors, v1 and v2, and I get a number that is an element of the field f. So the final result is an element of this underlying field of the vector space. So I can take two numbers and produce another. I can take two vectors and produce a number. So if I took two complex vectors and I was dealing with a complex vector space, I would end up with the inner product is a complex number. The inner product of two vectors in a quaternionic vector space, the result would be a quaternion. Now look, I don't hesitate to repeat myself, but we have to understand the vector space V has, say it's in 4 dimensions. It has E1, E2, E3, and E4 are the symbolic basis vectors. The field is not the value of the vectors. The field is the value of the scalars in front of the vectors. So any element of that vector space, say V1, it's going to be V1, say, superscript 1 E1 plus V1 superscript 2 E2 plus V1 superscript 3 E3 plus V1 superscript 4 E4, where these guys, V1 alpha, they're all elements of the field. So the complex numbers are these coordinate values. The components of the vector are complex, right? That's what we mean here. This inner product has got to deal with how the basis vectors are connected. So as with always, if we can define the inner product between E mu and E nu, if we know what this number is for every mu and nu, we can figure out the inner product for everything. So this is sort of what we have to provide. We have to provide, I shouldn't make it look like that, it looks like a matrix. We have to provide all these possible combinations of basis vectors, and we have to provide these answers. And if we can provide that answers, that's equivalent of defining a metric in this particular carrier space, right? So let's see. So the first rule for an inner product is that it must be linear over vector addition. This is vector addition. Beta is an element of the field, and beta v3, that is vector scalar multiplication, right? That's the scalar multiplication that lives inside the vector space itself. So that clearly is a vector, that clearly is a vector, adding them together is a vector, and then I can take the inner product of v1 with the resulting vector. And that has to be linear over this addition, meaning it has to equal alpha times the v1's inner product with v2 plus betas times the inner product of v1 with v3, where this is a number in the field, right? But if a field has its own multiplication property, so alpha times alpha is a member of the field, and v1, v2 inner product is a member of the field, right? So that product is just using now the field multiplication. So right there is the field multiplication. So you actually right here, you might write, oh, that's vector multiplication. So vector multiplication is this green thing that belongs to the vector space. Field multiplication might be the blue thing, right? That's field multiplication here. So it's kind of interesting to sort of track all this. Also note that it's very important that the alpha and beta are defined on the second element of the pairing, right? Here's the pairing v1, v2. I put alpha and beta on the second element, and it comes out on the left side, right? It comes out on the left side. In this study, unlike the study we did before, we track that. We track that very carefully. If it comes out from the left, it comes out on the left side. Because remember, quaternions are eligible here, right? We could do this with quaternions. And they're not really a field, right? Because they don't commute. So the fact that alpha is defined to come out on the left and this guy on the right matters if we're dealing with quaternions. It won't matter that much if we're dealing with these two, but it does matter if we're dealing with quaternions. Okay, so that's the first thing that an inner product metric has to obey. Well, if it matters and if we're tracking it, then I have to define it for the other side, right? I have to say, well, is it only linear in the second one? It's got to be, what about the first one? Well, the first one is where some of the magic happens, right? Because it could go the obvious way. The first one we could define very similar to this, but we put alpha and beta on the other side, right? We could do it exactly the same way, but now we track, for the sake of the darn quaternions, we put beta on the other side, right? So this, if this is the rule we choose, if this is the way the inner product works, because we have another option, which I'll show in a moment, then we call it bilinear. It's bilinear. So this is the bilinear version. I'll write that down. That's bilinear. The other choice is called sesquilinear. And this is how a sesquilinear it works the same as this bilinear rule, but now I pull out the conjugate. And this ultimately is all designed so that the magnitude of things is real, but the point is that a metric can be bilinear or it can be sesquilinear. And but it always has to obey this first rule, right? The first rule is always the same. It's the second one. It's when we put it in the right side. How does the other one handle? Now, some books define it exactly the opposite. They put this. They define the bilinear and sesquilinear part to be acting on the second half. I think there's a rough distinction between physics books that describe this and pure math books that describe it. They seem to tend to do it opposite. But regardless, it's just a matter of notation. But we're going to stick with Gilmore's notation. Okay, so now we know we have bilinear metrics and sesquilinear metrics. Are there any other rules that we have to abide by? Well, the answer is no. However, it's important to know that when you look at other definitions, you may see circumstances that insist that the metric is greater than 0. Right? That's not relevant for us. It also, there's sometimes we have to have, it's symmetrical, right? V1, V2 equals V2, V1, right? That's not required for us either. Sometimes this symmetry for the complex vector spaces will look like V1, V2 equals V2, V1 conjugate. These are all meaningful in different places, right? And in physics, this is very common because, in fact, in general relativity, that holds. This first one holds because they're real vector spaces. But for the general stuff we're studying, that's not necessarily true. We're not totally fixated on that. We're not going to study every possible metric in the world either, but the point is we can get by understanding the classical groups with just these rules alone. Now, after presenting this, what Gilmore does is he does a mini class in tensor index gymnastics. I'm going to assume you know a lot of this from what is a tensor, but the way this has to work is that like I said earlier, in order to define the inner product, I have to provide you with. Did I write that down anywhere? I guess I didn't. I have to provide it's in order to define an inner product, I have to say what E mu, E nu is for every value of mu and nu. So in a four-dimensional vector space, I have to write down E1, 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 E2, E1, E3. E1, 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 E2, E1, E3, 1, 2, 3, and then E1, E4. And then I have to write down E2, E1, E2, 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 E3, E2, E4. And if I do this, I'll have every possible matrix or inner product of all the basis vectors. And using this little table and these facts here, these two facts here, I can calculate the inner product of any two vectors that are expressed in the E mu, E nu basis. So these numbers are the key. And the numbers are, I'll write them in blue, we give them special symbols so we don't have to write them out this way. We call it G11, G12, G13, G14, and G21. There, I wrote them all out. Now, those numbers are it. With those numbers, you can calculate the inner product of any two vectors. Now, for those of you who've gone through the What is a Tensor class, you recognize this. These numbers, these are the components, G, alpha, beta, of the tensor, of the two, of the, let's see, I guess it would be the E alpha tensor product, E beta, right? It's a 0-2 tensor, right? These are the components of a 0-2 tensor. And that 0-2 tensor is designed to mimic the inner product. Now, Gilmore doesn't go into this that way. We just consider this an inner product of vector spaces. We don't create tensor product spaces for this purpose. General relativity's math just emphasizes this. It's got the same, this is all the same stuff, but it's just emphasized in a way that involves using tensor product spaces. Here we don't. We just use the component as a way of calculating the inner product of two vectors. So you won't see this kind of notation during much at all during this course. From time to time I'll throw it in just to make the connection. But now we just have to understand these G's as table entries to help us calculate inner products. We do, however, use the same sort of index gymnastics that we used in the past, right? So if I say that a vector V in our vector space, I guess I should do a vector little v in our vector space, I can define it as, well, let's see, I'll have to put a little arrow over it, and I'll say V sub I, E sub I, right? And the implied Einstein sum exists, so this equals V0, well, let's see, what do I want to do? I want to do it as V1 E1 plus V2 E2 plus V3 E3. Let's just do three dimensions. So I can write a vector V that way. I can write a vector W as Wi or Wj Ej, and then I can write the inner product of V with W as the inner product of Vi Ei Wj Ej. And because of this linearity principle, I can then pull these things out. I can pull the W out front, because remember the rule here is that the guy on the left, those coefficients come out on the front right? So I gotta go, oh shit. I gotta go W, J, V, I, E, I, E, J, like that. Even though the summation is still in effect, because remember, this is just a number. Those indices will cancel. That indices will be left over, so then I can just sum over all the different EJs, right? So the summation notation survives pulling the W out. The V, however, has to come to the other side, right? So WJ, EI, EJ, but the VI will come out with a conjugation, right? Now, it's safe to do the conjugation no matter what, because if V is a real number, then it'll be automatically bilinear because the conjugate just equals the number itself. But if you're dealing with C, or if you're dealing with the complex numbers of the quaternions, you want to have this conjugation in there. So we'll just put the conjugation in to be general. And then I ultimately replace this with Wj, Gij, Vi conjugate, like that. Now Gij, this guy here, remember the inner product is not a real number, it's a member of the field. So this could be a complex number, could be a real number, a complex number, or a quaternion. So you see how the ordering is important. These three could be three quaternions, in which case the ordering is significant. If I pulled the V out front, I'd have a different order. Notice the number is fixed no matter what because it's associative. See how important associativity is? I can do this or that because quaternions are associative. And because of that, there's no ambiguity as to what this means with quaternions. But I have to have very strict rules about how things land when I pull them out of structures like this. Otherwise, I don't know what I mean. So that's why we've come up with very unambiguous rules for these processes. Okay, and while we're on this topic, now we step into the thing that's of critical importance in understanding our classical groups. How do we transform this guy, who's really a matrix? This is in a sense, it's got two lower indices, so it's hard to call this a matrix. But how do we transform this metric? How do we transform this metric if we were to transform the basis of the underlying vector space, right? So, the whole vector space we're dealing with is V sub n, and we're keeping it general, R, C, or quaternions, right? So say we made a change of basis there. How would that work? Well, what does a change of basis look like? Well, we remember that we have E. How does this work? This goes E prime sub I is going to be some matrix, and that matrix will be AI alpha E sub alpha, right? So I have the original basis here, and the ith component of the new basis, or the ith basis vector of the new basis, right? There's no components, right? It's the ith basis vector of the new basis. I don't like primes, so I'm going to do a hat. Okay, that's the new basis. That ith new basis vector can be expressed as a linear combination of the old basis vectors. And I can, as I go through I can get every one of them, and this guy here is clearly a matrix. And that matrix is an element of, as we've defined it, we've literally defined it as the general linear group of n dimensions of some field, and that field would be whatever the underlying vector space's field. So Vn, the basis of Vn, is going to be E alpha, or that's one possible basis. The other possible basis is E hat I guess. Yeah, the alpha and the I, of course, don't really matter there. So this change of basis is critical. But now, because I know how these inner products work, I can tell you how the inner product is going to change if we change the basis. So let's have a look at that, right? We start with, all right, the inner product of, I guess what I'm curious about is I know that EJ, not EJ, EI, EJ, inner product equals GIJ by definition, right? That's the definition of GIJ. So I know if in a new coordinate system, I should be able to write EI hat, EJ hat equals GIJ. So it's a different collection of numbers in this new basis system. But I know that that's got to equal A I, well, wait a minute. Let's see, AI alpha, E alpha, and AJ beta, E beta, right? So this is just EI expressed in the old basis, and this here is EJ expressed in the old basis. But I know how this works because I know the rules. And so I pull this number out in front, and I push this number out to the other side. So you got to go the opposite way. And this guy will come out with its conjugation, which I'm using as a bar, so I don't have like superscript star, right? So I just put a bar for conjugation here. And this is the new expression, which is easily written as AJ beta G alpha beta AI alpha conjugate. And so I can write Gij hat. Now it's really, really tempting to make the obvious inference here that I can now write AJ beta AI alpha G alpha beta. And here you discover what we had done in the previous work on in our series on tensors. We see that this is exactly the transformation properties of the components of a 0, 2 tensor, right? But notice I switched the operations here. Oops, I forgot my bar there. I switched the operations here. So you can't do that for quaternions, right? So if this was quaternionic, that wouldn't really be allowed. Therefore, we will abandon that last step, right? We will get rid of that, and we will leave the result like this, okay? So this is the way our things are going to transform, our metrics are going to transform in full generality. Remember, if you're dealing with something that that's real, that doesn't have a conjugate, then the conjugate just is the same. Complex numbers for sesquilinear metrics, you would have this conjugation. But now this brings us to a very key point, and I will leave this. We'll end this lecture on this last topic. That's the critical topic, and so we'll be repeating it again next lecture. So this will be the second time you hear it the next lecture. The question is this: if I write down that Gij hat equals Gij, then what I'm actually saying is that the inner product of Ei hat with Ej hat, that number equals Ei Ej, meaning that the inner product of the basis vectors of the old basis and the inner product of the basis vectors of the new basis are the same. And this, by the way, does not have to happen. There's nothing that says if I just make some arbitrary transformation of the underlying vector space, meaning I change the basis in an arbitrary way, there's absolutely no reason that this number here, that Gij, is going to equal the result of this sum. Remember, I have a sum over beta and a sum over alpha here, right? The result of that sum for G12 is not going to equal the number G12 in the previous basis, right? There's just no reason for that to happen. On the other hand, it can happen. There are matrices A and B which do in fact preserve these numbers, right? These numbers are preserved through the transformation of the basis. And that is a really, really important point to understand. And mathematically, we write it down like this. I start with the basic formula. That's this guy right here, right? That's this formula. The formula for the change of the metric. I guess I'll call these the metric. I'll call it the metric. The change in the metric, where we understand the metric to mean this entire collection of values, right? The metric is this entire collection of values on the vector space. Remember, this is all in the carrier space, right? Now, that's a good point. The metric applies to action in the carrier space. These guys are, of course, members of GLNF, right? And I'm being very general about F, right? That's one of the beauties of this, is I don't have to specify the field. I can talk about this in generality. So I can write that down, but now I can further insist that this equals, right? This equals GKL without the prime. Actually, I don't like primes, right? I'm doing carets now, right? So it equals GKL without the carets. That means the numerical value of the metric in the new coordinate system is the same as the numerical value of the metric in the old coordinate system. Is that logical? Well, I have to choose A to make this so. So the way I look at this is, okay, I want to show, so we're going to assume that there are some A's out there that do this, that preserve metrics. So the idea would be like if you have a stick floating in space, and you measure the ends of the stick in a certain coordinate system. Now I change the coordinate system using a pure rotation, right? Well, the length of the stick, its measurement in that new coordinate system is not going to change because the coordinate system was rotated, right? So the metric that indicates sort of the length of things is, so there are rotations. So rotations would be an example of a transformation that's going to preserve the metrics in that particular case. And we'll actually cover that case very specifically later. So I want to show that, say I have two such rotations or two such transformations, A and B, that do in fact preserve this metric, right? They do in fact preserve the numerical values of this metric. Well, if that's the case, then I can now write another expression. I can write GMN, which is a further transformation, and it's a transformation of this to yet another coordinate system, which would basically be BNL G hat KL B MK bar, right? So that would be the next transformation, right? It would be B and A both preserve this metric. So independently, I can write these two expressions. But now, of course, I'm going to substitute this expression in for that. And what do I get? So I need to add this part, right? G, the second transformation, equals the value of the same in the first transformation, which equals the original value of the metric. So the metric's not changing. The metric value, G11, G22, G33, G32, those numbers are not changing as we use A and B. That's the definition. A and B are such. We've chosen them such that the metric doesn't change. And by enforcing these equalities, that's how we enforce that fact. So ultimately, this guy is going to equal this string here. But then if you look at this, that is literally how matrix multiplication is indicated, right? If I'm multiplying two matrices, A and B, I literally write, I sum over the inner indices, and that is matrix multiplication, right? So this guy equals a matrix that we could call AB, whose indices are N and J. So this guy is going to be B, A, we'll do it that way, N, J, G, I, J, and the other one is going to be, wait a minute, the other one's going to be AB, A, B, A, B, oh yeah, forgot that step. You gotta swap these two, right? So these are conjugates, so we have to use the old matrix rule that A conjugate, B conjugate equals B, A conjugate, right? So this is going to end up being B, A, right? And then it'll be M, I, but conjugate, the conjugate matrix. Now you might think, oh, wait a minute, you commuted two matrices here to do that, right? What about the quaternions? But the quaternions actually obey that rule. The quaternions, it turns out, obey the rule Q1, Q2 times 2Q conjugate equals Q2 conjugate Q1 conjugate. So that rule is obeyed by the quaternions. So if these were quaternionic, it would still obey this rule. So as long as the matrix is sesquilinear, right, as long as you do in fact have a sesquilinear metric where these conjugates appear, this will work for quaternions. However, if you don't, and there are no bars here, right, if it's a truly bilinear metric, right, in other words, if you have a bilinear metric, where is that down? I don't think. If you have a bilinear metric, but a quaternionic vector space with a bilinear metric, this little demonstration fails at that step, right? You can't do that. So here we are actually we're now forced to assume bilinear metrics for the circumstance of quaternions, if we want to include them. If it's just real or complex numbers, they commute, so that's okay no matter what. But with quaternions, it has to be sesquilinear for this to be true, right? So that's an important point. I should have made that. I should have pointed that out, I guess, in the quaternion section, but it would have seemed like a pretty random point to make. But now here it actually has meaning because you're seeing this development. So anyway, so what is this saying? Well, what this is saying is that, remember, this whole thing equals G hat M and equals G M N, right? So the point is if you now look at this last step, it looks like a single transformation from GMN right to G hat, double hat, using the matrix product BA, right? And if that's the case, because that's exactly the formula, the original formula, where A is now replaced by another matrix BA, which is just the product of A and B. A and B are both assumed to be such that the metric doesn't change. But the product of those two is also true, that the metric doesn't change. That the point being is that if I look at the set of all matrices that do not change, that leave this metric unchanged, this, in this case, this sesquilinear metric unchanged, then it's closed, right? It's closed, which gives us a hint that it may in fact be a group. That is the set of all metrics, the set of all transformations that leave a sesquilinear matrix, a sesquilinear metric unchanged under a basis transformation. That set is closed, so it has a shot at being a group, right? Closure is like the first principle for a group, a closure under a group operation, the group operation being matrix multiplication. And that's where our classical groups ultimately come from. I will show next time that this set of all matrices that preserve the form of the metric, right? In this case, the sesquilinear metric, not only are they closed, but they include inverses, they are associative, and there is an identity, and voila, you've got a group. And it is a group. In every matrix, it's a transformation, so it's a group contained in the general linear group. So it's all a subgroup of the general linear group. And that's what all of those different exotic groups that you see, the orthogonal group, the unitary group, the special linear, the special orthogonal, they're all forms of transformations of bases that preserve different kinds of metrics. And what are the different kinds of metrics? Well, at a minimum, we have bilinear and sesquilinear, but the other two properties we have are symmetric metrics, where this property does hold, where some version of these two hold, and anti-symmetric metrics, where you have a minus sign in there. So between bilinearity, sesquilinearity, symmetry, and anti-symmetry, we have basically four different kinds of metrics to think about that can be preserved. And the different transformations that preserve those metrics will ultimately form the different variety of classical groups. Okay, so I think that covers it for today. I'll see you next time.